Okay, welcome to Radcliffe. My name is John Huth, and I'm a professor in the physics department here at Harvard, but I'm also a member of the Ventures faculty, and it is a distinct delight to be able to work and help the programming at Radcliffe. And I get to bring science lectures and a science symposium every year to Radcliffe, and it's wonderful to talk to and put together the program because I'm able to target areas that I'm interested in and get experts and talk to the experts at just the right level so I can learn something new. And today is a perfect example of that. So it's a pleasure to introduce Kerry Emanuel. He's going to talk about hurricanes, and the title is Predicting and Adapting to Hurricane Risk. I've been fascinated with the issues of what's happening to our planet, and in particular, as the science topics may reflect the role of the ocean and climate and what it may be doing to us. So to just confess to a certain scientific geekiness, about once a week I check out the National Oceanic and Atmospheric Administration's website for the chart of the sea surface temperature anomaly, and sometimes even paste it up to Facebook once a week, as some of my Facebook friends know. So that gives you an idea of where I am on the nerdy spectrum, but that's me. So I'm hoping to hear a little bit more of this. So Dr. Emanuel is the Cecil and Ida Green Professor of Atmospheric Sciences at MIT, but is also the co-director of the Edward Lorenz Institute at MIT, and I could give you a lot of his background, but then you'd have to listen to all the honorific titles associated with him. But I will note, among other things, that he's has written a biography of Edward Lorenz. And Lorenz, for those of you who may not know, is credited as being the founder of chaos theory, and also there's this famous quote from him, does a butterfly's wings flapping in the Brazilian rainforest create a tornado in Texas, which has sparked, I use this in my lectures, and in fact I'm lecturing on weather today. So without any further ado, Kerry Emanuel.
Well, thank you very much, John. It's a great pleasure to be with you here today to talk about one of my favorite subjects. I go around the country talking about climate a lot, but I really like talking about hurricanes. So what I want to do today is to put a little bit of twist on this topic by not talking about the storms themselves that much as I'd like to, but talk about how we go about assessing risk from them. So I want to answer questions like, what's the probability that my campus, MIT, will someday be underwater in a flood? And is that probability evolving over time because of climate change? How do we go about answering those questions? And so that's what I'd sort of like to do with you today. So I'm going to start off talking a little bit about hurricanes themselves and the various risks that are associated with these storms. Then the real issue for me is, how do you quantify the risk? How do you actually put a number on it? I mean, how many years typically go by before we get hit here in New England, for example? And then to talk finally about how we expect climate change to begin to affect these storms. Just so you know what we're talking about, this is a classic satellite image of a hurricane that's been doctored by the people at NASA to give it a kind of three-dimensional perspective. So when you look down from space, you see a swirling mass of clouds a few hundred miles across. And the heaviest wind, the strongest rain is in an annulus that encloses often a clear area we know as the eye. When you look down from space, you're looking at the top of the storm about 12, 13 miles above the ocean surface. And you may not know this, but the temperatures up there are well below minus 100 degrees Fahrenheit. It's a remarkable thing that if you look through the whole atmosphere, some of the coldest air you can find is in the tropical upper atmosphere, colder even than Antarctica. And one of the reasons that hurricanes are so deadly and intense has to do with the fact that the atmosphere is so cold near their top. It actually makes them into very efficient heat engines. Now, if we zoom in, this is a photograph taken from the space station of the eye of Hurricane Igor. And once again, you see this annulus. We call it the eye wall for reasons that I'll show you, but you can see if you go down into the eye here that it is almost like a circular wall. We fly airplanes into these storms fairly routinely and have since the mid-1940s. But once again, the strongest winds, heaviest rains are under this annulus. In the northern hemisphere, the airflow is counterclockwise near the surface, but as you get to the top of the storm and the air begins to move out, it actually reverses rotation and goes the other way. And the rotation at all levels is reversed in sign in the southern hemisphere. This is just a little climatology of these storms showing tracks of tropical cyclone. Tropical cyclone, by the way, is a generic word for this kind of event. And hurricane is a strictly regional name that has a very interesting etymology. If anybody wants to talk about it afterwards, I can tell you something about that. But here is the sort of a global pattern of these storms. And most of us are familiar with the Atlantic storms here that typically form off Africa all the way westward over the Caribbean and the Gulf of Mexico, and they curve up. The colors are an indication of their wind speeds. But only about 12% of the world's tropical cyclones occur in the Atlantic. The rest occur in the Pacific and Indian Oceans. And they don't get quite as much coverage in the news as the Atlantic storms, but the most active region is in the Western Pacific. They just had a horrible typhoon, category typhoon, go into the northern Philippines last week, for example. And there are no tropical cyclones within a few degrees latitude of the equator, because you need to be able to take the Earth's rotation axis and project it onto what you locally call up and get an answer that's not zero. Well, right on the equator, it's zero, so you can't have any hurricanes there. So if you fantasize, as I sometimes do when I'm sitting in my office, about someday sailing around the world in a nice sailboat, and you're afraid of tropical cyclones, you just stick to the equator and you'll be fine. You may have other problems, but not that problem. Okay, so when we think about risks, we like to think about three major kinds of risks that are associated with hurricanes. What everybody thinks of is wind. The wind blows very hard, and structures aren't necessarily designed to cope with winds in this country much over 100 miles an hour, and they fail. And that is a big source of damage, but it is surprisingly not by any means the most lethal form of damage, particularly in the developing world. Actually, the second deadliest aspect of hurricanes, which I'm constantly, and my colleagues are constantly trying to drum into the public, is this boring thing called rain, right? The Weather Channel doesn't usually send their weather forecasters out to stand in a rainstorm because it's boring. They want the drama of the wind. But this is what kills, all right? And we have, unfortunately, lots and lots of bad examples of that, even recently in US history. But if you go back to 1998, Hurricane Mitch, which went into Central America, killed about 12,000 people. 12,000, okay? It was all from freshwater flooding caused by rain. One death occurred because of wind in that event. But historically, the most lethal is a storm surge. This is what got people in New Orleans and Katrina and New York and Sandy, but tragically in other parts of the world, like the Philippines a few years ago when Haiyan went in. The storm surge is what people find most difficult to envision. And so to try to get you to understand what it looks like, I'm going to play you a short film clip. And what you're going to see is a storm surge associated with Haiyan, photographed by an amateur who happened to have a video camera. And hydrodynamically, it is the same thing as a tsunami. It's just that it hasn't been caused by shaking earth, but by blowing wind. But when it happens, it's the same thing, except that it occurs in the middle of a typhoon. So this is a storm. I think you can imagine that that's impossible to survive if you're caught in it. That's what kills the most people. And yet we're forever trying to get people to take that seriously. And I think it's partially because they can't envision it, that they don't take warnings of this phenomenon all that seriously. So if you can imagine a tsunami in the middle of a typhoon, that's what a storm surge is. So we want to try to quantify, to actually put numbers on the risk of storm surges in different parts of the world. Now, if you just look at the damage from hurricanes, globally, on average, it's about 10,000 people a year. Of course, these are concentrated in a handful of events every few years. And 700 billion in 2015 US dollars annually. Okay, so that's a lot of money. And globally, this is the partitioning of insured losses for a particular year, 2006, by natural phenomena, the floods, 79% windstorms, of which most of that is hurricanes, and other phenomena. Now, this can be a bit misleading, on the other hand, because private insurance in most countries doesn't cover earthquakes and often doesn't cover floods, but it usually does cover hurricanes. And so for that reason, the big insurance companies and the reinsurance industry is pretty much paranoid about hurricanes, and they're always after me and my colleagues to tell them more about them. We have a big problem with hurricanes in the United States, a really big problem historically, and it's indicated in this graph, which shows the damage in 2004 US dollars, corrected for inflation but not otherwise corrected, by decade, from the first decade of the 20th century to the first decade of the 21st century. And you can see this really, really big increase in damages. It's sort of going up geometrically. And there's no particular mystery, on the other hand, about why that's happening. And it's not because hurricanes are changing, or at least not changing enough to cause that. It's just because coastal populations are going up much faster than the population as a whole. Okay. This is the population of Florida from 1790 to 2004, and you can see this huge increase. It really began to accelerate in the 1950s thanks to the invention of the air conditioner, which made Florida habitable by mere mortals. But that's the big problem. And policies that are in place in the United States actively subsidize people to move to and build in dangerous places. And that's going to cause a string of Sandys and Katrinas as far as the eye can see, having nothing to do with climate change. Climate change just makes it worse. In the United States, we have a huge hurricane policy problem. Now, my colleague Roger Pilkey at University of Colorado tried to correct the damages to account for changing population and infrastructure in addition to changing wealth, and gets this sort of normalized graph of hurricane damages. You can see the spectacular damages in the 1920s. That was largely from one event, the Miami hurricane of 1926, which put that city underwater. But the first decade of the 21st century is also very bad in this rank. Now, here is the US damage over that whole period of time by the category of storm at landfall. The Saffir-Simpson category is a measure of how strong the winds are, basically. You probably are familiar with this, but you can see most of the damage is done by category 3 and 4, and to some extent category 5 storms. But those storms are in a pretty small minority of events. So this is just the number of events whose landfall category is given on this axis. So most of the storms making landfall in the US are category 1 and category 2. They're relatively weak and they don't do very much damage. We're pretty hardened to those storms by now. It's the rarer, much rarer category 3, 4, and 5 storms. So here's the nature of the problem. More than half of the normalized damage over the last 150 years is done by 8 storms. 8. Okay? That's not a lot of numbers to do statistics with if you're a statistician. And more than 90% are caused by storms of category 3 and higher, which only constitute 13% of the events. So the conclusion that we get, and that we try to drum into the insurance companies, is all you want to do is do it from an actuarial basis, look at historical statistics, determine everything, like your property insurance premium, based on that. It's a fool's game. The history isn't long enough. And I haven't even started to tell you how imperfect that history is in terms of the quality of the data. So is there something we can do to put some more teeth onto this whole problem of hurricane risk? Can we do a better job than just looking at historical statistics? Well, yes, I think we can, and there are two main approaches. One is to ask, what can we learn from the geological record? Do hurricanes leave a signature in that record? And what can we learn from that? Now, this is not work that I do, but it's work that I strongly support. This field is called paleotempestology. And in fact, my only contribution to that field was to invent that word. But there are various techniques, and probably the most published one is this, that I just showed you a film of a storm surge. And if you imagine a coastline, of which you find many examples that are like this in the US East and Gulf Coast, where you have the ocean here and a beach, a bunch of sand dunes. And then behind that, you often have either a marsh or a lake or a lagoon or both. And normally, during quiescent periods, you have things growing in the lagoon and in the marsh, and they die and they settle down, and they create this very nice, rich, organic mud. But when there is a hurricane, the storm surge washes some of the sand into these marshes and lagoons. And then you resume burying it with organic material. So if you get a rubber dinghy and load it up with graduate students and go out in the lagoon and take a core, you can see these sand layers. And you can radiocarbon date the mud around them, and that will tell you when those sand layers were put down. So this has been done and is still being done around the country, and we're really beginning to learn some interesting things. I'm going to show you one site, which is at the head of Appalachia Bay in Florida here. The star is, where there was a kind of a sinkhole and sand being washed into the sinkhole by hurricanes over a period of time. And so we get a record that looks like this. So this is going back in time. So this is 2000 BC. This is 0, and then this is the present, 2000 AD. And each of these spikes, which represent how coarse the material is in the core, it's sort of a measure of how much sand you have, is denoted by is here. And some of the more recent ones correspond to known historical events. There's Elena that went ashore there in the 80s, Dennis more recently. And then back in the 18th century, there was a famous storm that wrecked an entire Spanish fleet, commanded by Solano, so it's called Solano Storm, and that shows up in this record. But you can see that there are periods, for example, the first 1,000 years BC, where there was a lot more activity. Also during the sort of medieval warm period in here, there was a lot more activity. And so we think, just based on that we're underestimating long-term hurricane risk in that particular place today because we happen to be in a relatively quiet period, okay? So that's one way of doing it, but that only gives you a few points along the coast. It doesn't really tell you what's happening globally. And so we turn to another technique, which is to try to bring physics to bear on the problem. After all, we do understand quite a bit more than we used to about how hurricanes work, to the extent that we can simulate them with models. But there is a technical problem with this. So if we try to use a climate model, for example, a global model to simulate them, it turns out they're just too coarse. These equations are solved on a computational lattice whose computational points are typically 100 miles apart. And that's just way too much, too coarse to resolve the critical eye wall region of a hurricane. In fact, we know from lots of experiments we need to be down in the 1 mile range of our computational grid to be able to simulate hurricanes accurately. So if you go ahead and try to do it, you get kind of bad answers. So what you see on this chart is wind speed. Now this is in meters per second. If you like knots, if you're a sailor, if you double this, you'll just about get knots. And this is the frequency of storms with this wind speed. The black is what we observe in nature. This black line is the division between category 2 and lower and category 3 and higher. And the red is what's modeled by global models. And so what this tells us is that the destructive storms, remember, are the ones to the right of this curve. These storms here, we don't even model those. So the very storms we're interested in, we can't simulate with a global model. Now, maybe 20 years from now, given the advance in the speed of computers, we'll be able to do that. But right now, we can't do it. We only can simulate weak, sort of sloppy storms. And that's with a state-of-the-art climate model. So global models don't simulate the destructive storms. So what we've done at MIT is an approach sometimes called downscaling, where you embed within the hurricane model, the global model, a very specialized hurricane model. So this is one that was developed over the years, first as a laboratory tool, then it was adopted by the National Hurricane Center to help forecast, and still does help them forecast real storms. And I don't want to bore you with a lot of technical detail about this, but it has very high resolution, and it critically interacts with the ocean. You know, hurricanes stir up cold water from the depths, and that helps limit their intensity. And you have to simulate that if you want to do hurricanes accurately. So what we do is to embed these little baby hurricane models. There's a lot more to it than I have time to explain within the time-evolving fields produced by a global model or a global climate analysis data set. And we can generate hundreds of thousands of synthetic events that way. And of course, it's all very well and good to say you can do that, but how do you know you've got it right? Well, there you do have to use history to ask, do you get the right distribution of storms? So this is an example of a mere 1,000 tracks produced by this method, where we embed the hurricane model not in a climate model, but in a climate data set, an actual data set of the current climate. And it's similar to the tracks I showed you before. The colors are an indication of intensity. Now, of course, those of you who have seen hurricane charts, I expect you have, John, given your proclivities for looking at maps like these, but this looks pretty good. But of course, you want to do much more rigorous tests on this than you can do by once over lightly with the eyeball, but this is kind of a low-level check. And we've done lots and lots of statistics, and the technique works surprisingly well. This shows you the origin points of these simulated storms versus real storms. And you can see similarities and differences. The greatest differences are that there are a lot of storms in the observations up in this region here, including right off of Long Island. And we know that can't be true because tropical cyclones never develop off of Long Island. And it shows you that there are perils in doing this comparison. The observations aren't always right. The analysts put into the mix nor'easters, which are not the same thing as hurricanes. And so you have to be very careful about how you do these comparisons. Now, once you have this technique, you can filter storms. So that, for example, here are 200 hurricane tracks that happen to pass close enough to where we're all sitting today to affect the region. And then we can, if we're interested in hurricanes in Boston, we can produce event sets like this and start to really put some numbers on the risk. Now, what we like to do is to compare those statistics with historical statistics in places where there are enough historical data to make that viable. And that gives us some confidence that this works. So here is an example of a storm that affects Boston. It's just one out of many thousands of simulated storms. The color, again, shows you a measure of how strong the winds are. These are dates in September. So this particular event, characteristic of all strong hurricanes in New England, is moving very, very quickly to the north. It covers territory from off the Carolinas to New Hampshire in one day, so it's really moving fast. And so we can, here is something called a wind swath. This is just the contours of the strongest wind experienced at any point during this one event that I just showed you. So for example, in Boston Harbor, there are winds of 85 knots or so with this event, which is a respectable hurricane for New England. The vent itself follows along this. The center of the storm goes up this black line. And as usual for New England hurricanes, the strong winds are all to the right of the track, whereas a lot of the rain is to the left of the track. Speaking of rain, this model does produce rain. Remember, rain's the second biggest killer. We're worried about that. This storm was moving very fast, so it didn't produce very much rain, but here you see contours of storm accumulated rainfall in millimeters. So you can see the effects of topography and other things that are known to affect rainfall there. Well, the beauty of this is that we can go way beyond history in estimating things like the rare events. So here is an estimate of something called the return periods for storms affecting the whole New England coastline. And so this is the return period in years, and that's technically it's just the inverse annual probability of storms. So the way to interpret 100 is that a return period of 100 is a probability of 1% in a given year that you'll have a storm of that intensity. So we see that there's a 1% probability that you'll have a storm in any given year affecting the New England coastline with winds of around 105 nautical miles per hour. The green dots are inferences made strictly on historical data, and the blue dots come from these synthetic events I just described. And the red is just a curve fit to that. So you can get much further out because you have many, many more events. So you can look at much rarer events of the kind that usually cause the most damage. Now, I mentioned to you that the most lethal aspect, on the other hand, of hurricanes is the storm surge. So we haven't said anything about how to model those, but in fact, that is a very advanced, that particular bit of computational fluid dynamics is very advanced. My profession has gotten very good at simulating storm surges, given that you know what the hurricane's doing, obviously. All right, so if you have a known hurricane, you can do that. And here is an example of a series of simulations for the city of New York that we did some years ago. And this circular area here shows an example of the computational mesh that was used to do the surge simulations. And the dots, blue and red dots outside is a different model, a much more sophisticated one, which has an adaptive, an unstructured mesh. And the beauty about storm surge modeling is the equations are very simple for those of you who do any kind of modeling. On the other hand, the boundary conditions are hopelessly complicated. So it's an interesting computational challenge, but I think it's been largely met. So we can use these thousands of artificial hurricanes, if you will, to drive storm surges using models like this and get an estimate of the risk of storm surges. And we did a study for Manhattan back in 2010. It's before Sandy, actually. And this was our estimate of the peak surge at the Battery, which is at the southern tip of New York and happens to have a tide gauge. So these things are measured there. And this, again, is return period. So this is 1 in 100 years, 1 in 500 years, 1 in 5,000 years, 1 in 50,000 years. And this is the level of the surge in meters, okay? So Sandy's surge was about 2.8 meters. And so we would have estimated that that was like a 600 or 700 year event that we saw for the Battery. Doesn't mean you wouldn't have to wait that long to see a surge of that magnitude somewhere around there, but right at the Battery. And other people using completely different methods have come up with similar estimates. So Sandy was a rare event. And we did this before Sandy. All right, so we can do rain, we can do wind, we can do storm surge, and we're starting to try to put together what the actual risk is in places all around the world, including most recently in my own backyard. I finally got MIT to realize that they have a substantial flooding risk from these kinds of events, including the fact that the control room for our nuclear reactor is underground and not very far from the Charles River. So I'm trying to get them to pay attention to that, but slowly it's happening. Now, I want to talk about climate change, and I don't have a long time to introduce the subject. A lot of you have heard a lot about it, and I'm not really here to talk about that per se. But I did want to mention that this is an old subject, not a new one. And arguably the first scientist who worried about the fact that we were changing the climate was this man, Svante Arrhenius, a gifted Swedish chemist who won a Nobel Prize in chemistry, who lived at the end of the 19th and the early 20th centuries. And he wrote a paper in 1906 in which he, using measurements of moonlight and pencil and paper, this is good old-fashioned 19th century science, came to the conclusion that if we succeeded in doubling the carbon dioxide content of the atmosphere, we would raise the Earth's surface temperature by about 4 degrees C. And if we quadrupled it, it would go up 8 degrees. There were slightly higher estimates than ones he had done about 8 years before that, 9 years before that. But given that with all of our computers and the whole IPCC process, we're 2 degrees to 4.5 degrees is the current range. He did this without computers, with pencil and paper. It's pretty good. So was he right? I think the data are pretty persuasive about this. This is green curve is the Earth's mean surface temperature from thermometers going back to the late 19th century. And the blue curve is a measure of the carbon dioxide content of the atmosphere. And you can see that there's a lot of chaotic variability. John mentioned to you Ed Lorenz, who was very interested in this. There are also things I haven't shown you on this diagram, volcanic eruptions and so forth. But by and large, this surface temperature has followed carbon dioxide as we know it did in the geological past. So we have a problem. And a lot of work has gone into trying to quantify all kinds of risks associated with this, but I'm here today to talk about hurricane risks. Now, before I show you what this particular model has to say about that, let me say that all the way back in the late 1980s, we understood just from the basic theory of hurricanes as heat engines, just engines for taking, in this case, the heat energy from the ocean and converting it into the kinetic energy of winds, would have to go up if you warm the climate by almost any means you can think of, the sun, CO2, so forth. There's a speed limit for hurricanes that's dictated by the thermodynamics of that engine, and that speed limit goes up as you put carbon dioxide in the atmosphere. So we understood that theoretically, but there's an awful lot of other things that can change, the tracks of storms and so forth. And so we'd like to try to put some numbers on this. So what we do is we apply this technique I just described to you, rather than to climatological data sets, to global climate models. And we are using at the moment 7 models chosen because of the availability of the actual output we need to run our technique. And I'm going to look at, primarily compare historical period storms to end of this century storms under a kind of business as usual emission scenario. If you look globally, this is a measure of global hurricane or tropical cyclone power. This is actually a hindcast going back to 1980, and then this is a prediction going to the end of this century. And you can see that there is, in this shading, is a scatter among the 7 models that we applied this to. So you can see there's considerable scatter, but in general, there seems to be an upward trend, as theory told us there should be. So here is a very rare event that occurs in one of these models that affects Boston at the end of this century, 2086, in August and September. And so you can see that now, and again, this even then would be an extraordinarily rare event, but it's actually possible at the end of the century to get a Cat 5 hurricane in Boston, according to this. Unlikely, but possible. And there's the wind swath associated with that event. And the wind speed and direction on the 4th to 5th of September at Logan Airport. So wind is ramping up. This is in knots. It's a little bit more than a mile per hour if you aren't used to those units. It ramps up. It goes all the way up to about 130 knots. Then the eye passes over. And then this is the back side of the eye wall. But and this is the wind direction here. That's a very, very rare event. And that's an event that would not be able to happen physically in today's climate. So if we want to really try to get down to the nuts and bolts, This is showing, in this case, you have to adjust yourself. This is the return period here of storms of tropical storm, hurricane, Cat 1, Cat 2, Cat 3, all the way to Cat 5. This is the return period of storms passing within 150 kilometers of here, based on 5 climate models. The blue is for the climate of the late 20th century, and the red is for the climate of the late 21st century. So, for example, a Cat 5 passing within 150 kilometers in the current climate is virtually impossible. It's a 1 in 200,000 year event, 1 in 200,000 chance each year of having an event. It's basically impossible, but it becomes something like a 1 in 900 year event by the end of the century. The shading, again, is the scatter among, in this case, the 5 climate models that we applied the technique to. And so an event that's 100 knot of category 2 event, might be expected once per 100 years on the average. By the end of the century, it's more like once a decade. So there's a big change. I was a bit surprised to see that. Rain is much more clear-cut. As the air gets warmer, there's more water vapor in it, and a given storm can rain more. Doesn't mean that annual rainfall will go up, but you have storms that produce more rain. This is the same kind of curve. It's just for the total storm rainfall in millimeters. This, again, is for Boston, the current climate, the future climate. So a 1,000-year event at the end of the 20th century becomes, every 50 years or something like that at the end of this century. That's something that virtually all techniques show, is that the risk of really heavy rainstorms of just about any kind goes up in many places because of this phenomenon. This is the same kind of thing, but for the storm surge in Boston Harbor. So once again, this is the peak surge in meters. It's not as big as you can get in New York. This is for the current climate, and this is for the future climate, and this is all because of changes in the character of the hurricanes. We haven't put sea level rise into this yet, and that's a big deal, and I'll show you that in a minute. But for example, a surge of 2 meters in Boston Harbor is actually hard to do with a hurricane. We're more at risk of nor'easters in Boston. But by the end of the century, that becomes every few hundred years. But sea level is going up. So this is global sea level relative to what it was in 2000. Going back to 1980, this is in feet in this chart. That's what's happened, and that's what's projected to happen. So we could have a few feet rise in sea level, but with a lot of uncertainty. And unfortunately, it's going up faster in certain places, including New England, than it's going up globally. Sea level rise is not globally uniform. Far from it. There are actually places like south of Greenland where the sea level is falling. And so somebody might want to ask me a question later, why should sea level be falling south of Greenland? Okay, kind of an interesting story there. So if we build a 1 meter sea level rise globally, or in Boston, into that, and then we get these huge differences in surge, not surprisingly. So a 10,000-year event becomes, every couple of centuries, for example, in Boston. And an event that you might experience once every 500 years, you basically have it every year, because 1 meter is already built into the system. So it's there permanently. Now, once you have numbers like this, you can start to convert them into other things that you might be interested in. For example, monetary losses. And Michael Bloomberg and Hank Paulson and a few other people commissioned a rather thorough economic analysis of the costs of climate change a couple of years ago, and I was part of that effort. I sort of worked on the hurricane aspect of this, a very comprehensive report. So what we see here for the whole US is the increase in the average annual losses due to hurricanes. And this increase is in billions of dollars. So by 2030, we could have just maybe a few $billion increase over what we're already experiencing. The green is for, the blue is for sea level rise alone without any changes in hurricane characteristics, and the green includes changing hurricanes. So by the end of the century, if we include changing hurricane statistics, we're looking at an additional average $70 billion a year loss. And so planners are very interested in numbers like that. So let me try to bring it down finally to the level where it might mean something. What are you going to do about this? All right? So I'm not going to get into the whole issue of should we try to control climate change. If you're the mayor of a city, like the mayor of New York, that's not your problem. Your problem is how do you make the city resilient or robust to this sort of thing. So they've actually done a lot more work in New York than we've done here in Boston, and they've actually started to cost out various options for preparing New York City for this kind of thing in the future. So what you see here are some proposals. If you might recognize this as a map of the New York metro area. There's Staten Island, Manhattan is here, Brooklyn, and so forth. And so one of the options is to build some storm barriers. This is a fantastic one. It goes all the way from the Rockaways to New Jersey. Okay. There are much smaller versions of this all around the country, including most spectacularly at New Bedford, if you've ever been down there to see their storm barrier. But this is a really big version, and they have to build a small one up here at the head of Long Island Sound, and they shut those gates if a storm comes. And they've actually costed that out. I sort of helped them do that. And another strategy is to forget about doing that, build some much more modest barriers, but harden a lot of the infrastructure of the city. Make it possible to keep water out of the subways. Move generators from the basements of buildings to the rooftop, emergency generators, so they don't go out just when you need them and so forth. Now, what option you decide to do if you're a resident of the city of New York, a voter there, is a perplexing question because it depends upon your time scale and it also depends on your assumption about how the economics of the city and the country will evolve over the next 100 years, so that you know something about the discount rate. So I don't want to bore you with this, but these are sort of benefit-cost ratios for 4 different kinds of solutions. And this is for the current climate. This is for climate change. There are a lot of numbers up here. But the bottom line is, if you're only worried about the next 50 years, harden the buildings. And that's about the best you can do. If you want to take an optimistic point of view in terms of the economy and wait, then 50 years later, you build the storm barrier. And that will see you through the next 50 or 100 years. Now, again, voters have to decide this. It's our job, not my job, because I'm not an economist, thank God. But the economist's job is to understand how to convey to the public what particular benefit is going to cost what amount so that they can make intelligent decisions. All right, so I hope I've given you a little bit of a taste for where we're going. This is taking the physical problem of hurricanes. And hurricanes are really beautiful for physicists, okay? As deadly as they are, they're really neat phenomena to understand. I'd love to talk to you about that today. But I think it's important also to take what we've learned about physics and about modeling storms and actually start to use it to understand risk. And it's kind of an interesting thing to do because there are physical modelers over on that side of the room and there are risk modelers over the other corner, and they hardly ever talk to each other because the risk modelers are all doing it based on historical statistics. There were statisticians looking at actuarial approaches to this, right? And the physicists weren't worried about risk. They just want to know how the thing works. And some of us have tried to bridge this, and it's actually turning into a very fascinating endeavor. So let me summarize. Hurricane history, even in the US, where it's arguably the best historically, is too short. And I didn't really talk about it, but the hurricane records are pretty bad. So when you put those together, it's really tough to come up with quantitative assessments of hurricane risk strictly from historical data. You can make better estimates, although I'm not sure we're there yet. Potentially you can make better estimates by looking at the geological record and making deductions from that. There are other techniques I didn't talk about today which are even more fantastic for doing this. So there's some hope that we're going to learn something about hurricanes from looking at a 7,000-year history rather than just a 100-year history. And then in many places, hurricane risk is expected to increase through the century. There are places where we expect it to fall, but by and large, we see increases. Coastal impacts of hurricanes, whether they change or not, are made much worse by sea level rise. And I should say here that in the United States, we have a peculiar and very worrying problem that would be a problem if there was no climate change. It's the confluence of two bad trends, one of which is actually climate-related: rising sea level and big-time rising coastal populations, accompanied by policies that greatly underwrite the risk people take when they move to the coast. I love the sea, so it's a terrible dilemma for me, but the fact is that we're going to bring about lots and lots of more hurricane disasters just through policy. You know, we call them natural disasters, but that's not correct. Nature got used to these events a long time ago. They're disasters for us because we insist upon building stuff and living in dangerous places. That's the bottom line. If we're simply going to adapt to the changes, that pathway is very dependent upon where you are. What works for New York may be a disaster for Boston and vice versa. And also on your viewpoint. Is it you just care about the economy today, or do you care about the economy that your kids and grandkids will experience? So it's all a bit subjective. And from an economical point of view, also assumptions about discount rates. And hurricanes are just one of many problems that we have to try to understand in terms of their risk and how to mitigate them and adapt to them. So I'll leave you with those thoughts, and happy to take questions.